Welcome back to The Explainer. Today, we're jumping right into the cost of catching it late, part 2. We're going to be talking about an absolutely crucial, high-stakes phase of factory acceptance testing, and that is the mechanical verification. As a quick recap of part 1, we established that mechanical checks catch physical flaws that electrical tests simply can't. We also learned that lifting capacity absolutely must account for the weight of the oil, not just the dry metal. So for part 2 today, we're focusing on the vital safety margin role, and we'll look at a real-world near miss that proves exactly why this is just so critical.
Okay, so before a single volt is ever applied to a transformer, we actually have to physically validate it using a standard FAT mechanical checklist. You're checking the main dimensions against the approved general arrangement drawing. You're verifying the lifting facilities are correct, and you're ensuring that the equipment mounting and bolting facilities meet the exact drawing specifications. Why? Well, because under-torqued bolts will loosen under vibration, while over-torqued ones can literally crack the flanges. You even have to check the paintwork and surface treatment for acceptable finish and thickness. This is basically your structured proof that the physical reality of the unit matches your project documentation.
Now here is your absolute golden rule of thumb for lifting operations, plus 25%. Never, ever trust the nameplate dry weight alone. You always want to verify the lifting lug rated capacity against the total transformer mass, and yes, that includes the oil, plus a minimum 25% safety margin. Honestly, if the lug capacity doesn't clear that total mass plus 25% threshold, it is simply not safe to lift, period. You know, mechanical verification can sometimes feel like the boring or tedious part of a FAT, especially compared to the high-voltage tests. But think about it like this. It's exactly like measuring the doorway before buying a new sofa. Just imagine a transformer arriving on site and physically not fitting through the switchroom door. Or maybe it can't be lifted safely onto a marine topside because the crane is undersized for the actual dimensions. A dimensional mismatch that you discover after installation is exponentially more expensive and painful to fix than one caught during the FAT. Verifying your GA drawings against the actual site dimensions before the unit ever ships is going to prevent some of the most avoidable yet devastating commissioning delays. Let's actually look at a real-world case study. We have a 1500 kVA transformer. Now, while the dry mass, the core, the coils, the steel tank, takes up most of the weight, there is an 800 kilogram oil fill weight that you have to account for. In this specific instance, a unit arrived with perfectly correct electrical ratings, but whoever signed off on the mechanicals completely missed that roughly 800 kilograms of oil sitting right there inside the tank. And that brings us to a pretty terrifying reality: 800 kilograms of missed oil weight. Because most oil-immersed units ship or lift with the oil already inside them, the site's rigging plan had actually been calculated against the dry weight alone. If this discrepancy hadn't been caught just in time during a mechanical check, that rigging plan would have been dangerously under-margined. We're literally talking about a scenario where the lifting lugs could have yielded or just snapped entirely while the transformer was suspended in mid-air. It's a really stark reminder that what looks like a simple paperwork error in the factory can turn into a catastrophic physical hazard on-site. So let's lock this lesson in with a quick question. Why do we check the lifting rating against the total mass rather than just relying on the base dry spec on the nameplate? Well, it's because the shipped with oil mass is the real lifted weight. Rigging against the dry weight alone inherently risks exceeding the lifting lug's safety margin. Sure, the nameplate tells you the rating, but the total physical reality is what actually dictates the safety of your lift. Okay, so you now have the tools to understand and perform a highly structured mechanical verification. You know to check those GA dimensions, verify the bolt torque, and most importantly, calculate that lifting margin with the oil included. Next time in this Explainer series, we're going to pivot to the electrical side of physical compliance. We'll be looking at things like sealing, markings, and earth continuity. We'll explore why a single 2mm gap in a cabinet gland can fail an entire IP rating, how to verify correct terminal markings, and why a 5-ohm reading on earth continuity is a massive red flag. So ask yourself, if your transformer passes every high-voltage test but fails its earth continuity check, is it really ready to be energized? We'll find out next time.